Next, we're going to talk about the idea of a basis for a subspace. So let's assume that we've got some subspace first, fixed in the background. So call it H. Let's say H is a subspace of Rn. And we want to outline what it means for a set B of vectors, call them v1, v2 up to vp, to be a basis for our subspace H. So what does that mean exactly? Well, it means two things. First of all, our set B must be linearly independent. Okay, so that means the only way to write the zero vector as a linear combination of these vectors is to take all of your weights equal to zero. That's the only way to do it. Statement number two is really just saying that the vectors in B span or generate the subspace H. And there's nothing wrong with just taking this statement at face value. H is equal to the span of the vectors in B. That means if you take all the linear combinations of the vectors in your set B, take all the possible linear combinations you could form, you're going to end up getting exactly the vectors in your set H. Nothing more and nothing less. So let's go. I just want to go through that in a little bit more detail, okay? Because whenever you see a statement like this, there's actually two claims that are being made. First of all, every vector in H, if you take any vector at all that's in H, there's some way to write that vector as a linear combination of the vectors in this list. That's half of it. The other half is saying that it is impossible through taking linear combinations of these vectors to generate some extra vector that's not in H. You're also saying that that's not possible to do when you make a claim like this. Okay, so that's what it means to say that H is the span of the vectors in B. So if you have a set B that satisfies both of those conditions, well, then you've got yourself a basis for the subspace H. Okay, so what does this look like in practice? Well, this example is the canonical setting where this happens. Okay, and in fact, the whole notion of a basis is really just the generalization of this exact situation. Okay, so let's say n is some positive integer as usual, and you can consider Euclidean space Rn. This set of vectors, the standard basis vectors, e1, e2, all the way up to en. Remember how they're defined? E1 just has a 1 in its first coordinate, 0 is elsewhere. E2 has a 1 in the second coordinate, and 0 is elsewhere. Keep going all the way. E3 got a 1 in the third coordinate, 0 is elsewhere. And then your very last standard basis vector is En. It's got a 1 in the nth coordinate and 0 is elsewhere. If you take these vectors and put them together into a set, like we've done here, then that is a basis for Rn. In fact, it's such a special basis, it has its own name. It's called the standard basis for Rn. And hey, guess where those standard basis vectors get their name? From this, right? That's why we've been calling them the standard basis vectors, because they actually form a basis for Rn. And in some sense, they form the cleanest, nicest, most natural basis for Rn, which is why they're called the standard basis. Okay, so how do you know it forms a basis? Well, first of all, you have to check that these vectors are linearly independent. Okay, so that in and of itself takes a little bit of work. The next thing you'd have to do is check that Rn is equal to the span of these vectors. Okay, so I'm going to let you think about why that's true. But if you get stuck, I want to give you a hint too. So I want you to refer back to the previous section. And remember when we talked about the invertible matrix theorem? That was a whole long list of statements that were all equivalent in the sense that they were true under the exact same circumstances. There's two particular statements in that list that I want you to take a look at, and that's statement F and statement G. And it just turns out that these statements are exactly what you need. Okay, so I will leave that to you to think about, to verify why this is the case, why this set is a basis for Rn. But as usual, if you ever get stuck, or if you spend a few minutes on it, if you just don't see it, then just come talk to me. We'll figure it out. Okay? Now I want to focus on actually applying this notion and finding a basis for a particular subspace. Okay? And one of the things that's kind of neat about this is that any subspace that you encounter, particularly in this course, if you ever want to find a basis for it, as long as you know how to find a basis for a couple of different types of subspaces, in particular the null space and the column space. If you know how to find a basis for both of those subspaces, you'll be in good shape to tackle any subspace I throw at you. It's not that null space and column space is the only type of subspace that we're going to consider, but if you know how to find a basis for both of those types of subspaces, then you'll be able to find a basis for any subspace that I ask you to find a basis for. Okay, so how would you handle this? We've got a matrix A in this example, and we would like to find a basis for its null space. Remember what the null space of a matrix is? It's the set of all solutions to the associated homogeneous system. So what you're going to start by doing is you're going to start by finding the solution set to the associated homogeneous system. And what that would require, well, what's the augmented matrix for the associated homogeneous system? Well, it's going to look like this. You're going to take A, and it'll be your coefficient matrix, and then just take your constant columns to be equal to all zeros. Okay? And that's going to give you the augmented matrix of the associated homogeneous system. Okay, this is going to take some work to solve this, right? We have to do quite a few row operations. It's got 4 equations and 6 variables. Even if this works out nicely, which actually it does, it works out not too bad, it's still going to take at least half a page and maybe even more, maybe a whole page of work to actually row reduce this. So as usual, what I'm going to do is I'm going to omit those steps and just give you the conclusion. Okay, so once you perform the Gauss-Jordan elimination method and turn this into its reduced row echelon form, this is what you're going to get. Okay, so that'll be your first row. Then your second row will be 0, 0, 1, 2, 0, 0, 0. In fact, the constant column is going to be all zeros. And then your third row is going to be 0, 0, 0, 0, 0, 1. And then your fourth row is just all zeros. So I want to acknowledge the fact that I'm skipping some steps here. Okay, this is a fair amount of work to row reduce this matrix, but it is just row operations are kind of a distraction from the main point of this example. So that's why I don't want to get sidetracked with them too much. But now what we're going to do is we're going to write out the general solution. And notice that if we just jump right from a matrix to the augmented matrix of its associated homogeneous system, you don't actually have any variable names to work with. So let's just make an agreement. Let's say that these columns correspond to the variables x1 through x6, just so we have something to work with. You need variables to actually write out your solution. So now we'll start with this column. And you can see it is a pivot column because there's a leading 1. So you're going to write out the equation corresponding to that row. And what's that going to look like? You're going to have x6 is equal to 0. Actually, I'm going to slide this up so I have more room. Okay, then look at this column. That's not a pivot column. There's no leading 1 in that column, so you're going to assign x5 a parameter. Same with x4, right? x4, there's no leading 1 in that column, so you're going to assign a parameter to x4. x3, well, there is a leading 1 in that column, so the third column is a pivot column, so you're going to write out the equation that corresponds to this row. What's that equation going to look like? You're going to have x3 plus 2x4 is equal to 0. So let's write that out. x3 plus 2x4 is equal to 0. Solve that for x3 and plug in your parameter for x4, which is a t, and you're going to get negative 2t. Okay, and then let's move on to the next column, x2, and you see that's not a pivot column because there's no leading 1. So we will assign x2 a parameter as well. So x2, what's the next? We used s and t. Let's use u as a letter now for our next parameter. And okay, and then the last column, or the first column, if you start at the left, the x1 column this is a pivot column because it has a leading 1. So we'll write out the equation corresponding to this row, and you're going to get x1 plus 3x2 plus 4x4 plus 2x5 equals 0. So if I solve this for x1, I'll get negative 3x2 minus 4x4 minus 2x5. And if I plug in my parameters, I'll get negative 3u minus 4 times x4 was t, and then minus 2 times s, because x5 was s. Okay, so that finally now we've got all our variables solved for in terms of these parameters, s, t, and u. Let's write out the general solution. I don't need this anymore. Let's write out the general solution in terms of those parameters in vector form. Actually, I better slide down here so I have enough room to write this. So I'll write it as a column, x1, x2, x3, x4, x5, and x6. Okay, so what am I going to get? If I put these together in a vector, I'll have negative 3u minus 4t minus 2s, that's x1. x2 is u. x3 is minus 2t. x4 is t. x5 was s. And then x6 was 0. Okay, so that's the general solution to the system. But we're trying to find a basis for the null space. We're not trying to just solve this system. So we're not going to stop here. What we're going to do is we're going to decompose this vector. We've actually done this trick before. We're going to break it up into the sum of 3 separate vectors. And the reason we're doing 3 separate vectors is going to do one vector for each parameter. Okay, so I'm going to pick out all the terms that have u's in them for that vector. Then I'll pick out all the terms that have t's in them for this next vector. Notice I'm just putting a 0 for any of the coordinates that don't have t terms. And then at the coordinates that do have t terms, I just include only that term. And then here I'll do the same thing for s. So I'll have negative 2s, and then 0, 0, 0, s, and then 0. And then next, I'm going to, because I've split it up like this, now I can pull out those parameters. So the first vector, I'll write this as u. I'm going to slide down a bit because I didn't leave myself enough space here. I'll have u times negative 3, 1, 0, 0, 0, 0, plus t times negative 4, 0, negative 2, 1, 0, 0. And then for the last one, I'll pull out the s. So I'll have s times negative 2, 0, 0, 0, 1, 0. Okay, so now what? Guess what your basis vectors are going to be. These vectors are going to do it because, well, for half of it's obvious here, right? This is supposed to be the general solution to the associated homogeneous system, and we've shown that this vector the solution vector must be of this form. Well, what is this form? This is exactly the most general linear combination of these 3 vectors that you could ever possibly form. Now, it really just amounts to saying, are they linearly independent? Well, a quick check will show that they are. One of the things, the telltale signs of vectors being linearly independent is if each of them has at least one non-zero coordinate where the other vectors have only zeros. That's not going to describe all linearly independent sets, but in this case it will. Look at this one. This one has a 1 in the second coordinate. The other 2 vectors have a 0 in the second coordinate. The second vector has a 1 in the fourth coordinate, but the other 2 vectors have a 0 in that coordinate. And then for the fifth coordinate, look at the fifth coordinate, the third vector has a 1, and the other 2 vectors have a 0 in that coordinate. Whenever you see that situation, that's enough to conclude that the vectors are linearly independent. That's enough of a justification right there. Although you can always just use the definition of a linearly independent set of vectors and check that way too, right? Just if you wanted to check from scratch, how would you do it? You'd say, suppose that this is equal to the 0 vector. You would generate a system of 6 equations in 3 variables. You'd solve it and show that you only get the trivial solution. That would be the most bulletproof formal way to check. But in this case, I'll spoil the surprise, and this is a bit of a hack you can use whenever you're finding a basis for the null space. In fact, more generally, whenever you're finding the general solution to a homogeneous linear system, you're going to get something of this form, right? The more parameters you have, the more distinct vectors you're going to get at this stage, right? We had 3 parameters, so we had these 3 vectors that came out of this process. The vectors that come out of this process will always be linearly independent. I'll promise you that. Okay, so what does that mean? That means we have a linearly independent spanning set for the null space of A. I'm going to delete these arrows because they're not helpful anymore. So we can form our basis like this. So B, and we'll take, so the first vector is going to be -3, 1, 0, 0, 0, 0. The second vector, -4, 0, -2, 1, 0, 0. And then our third vector, -2, 0, 0, 0, 1, 0. That is a basis. For what? For the null space of A. All right, so that, let's put a box around that. That was a lot of work. So that is our final answer.